Thank you so
All right.
much.
Go ahead.
Awesome. Okay, well, so good morning / good afternoon / good evening, everyone. This is, I believe, unless we schedule something random, this is the last of the officially scheduled physics track lectures for week 0, which is, I'm sure, exciting / saddening for everyone, depending on how you found them so far. And so this is intended to be a kind of a very brief introduction to this framework that we've developed called MultiwaySystem, or now I suppose global MultiwaySystem, to distinguish it from the local MultiwaySystem that's implemented in Wolfram Model, which is it's a general tool I essentially designed for dealing with abstract rewriting systems of any kind, be they Wolfram Model systems, substitution systems, cellular automata, Turing machines, any other kind of system where there isn't a sort of canonical deterministic updating order defined. And so it's I hope, a fairly general, fairly abstract, fairly extensible framework that I hope will be useful to many of you in the projects that you're going to be doing over the next few weeks. And so I kind of want to give you a brief introduction to the multi-way-system framework and several other functions that I've developed or that we've developed that kind of go around it and plug into it in various ways. Okay, so let me just begin. By the way, I should apologize to begin with. If my sound quality is a bit weird, I was just telling Erin, it's an uncharacteristically warm day in the UK at the moment. So unlike normal, I have a desk fan currently pointed directly at my face, which you might be able to hear. I don't know, but apologies if you can. Okay. So hopefully you guys can see my screen, and hopefully you will complain at me if you can't and I didn't share the wrong thing like I did yesterday. Okay, so let's deal with the sort of simplest case of this. So if we call resource function, as with all of our functions, they're all in the function repository. You can call them you don't need to download anything. You can call everything just using the function repository resource system. So if we input a Wolfram Model rule, like, I don't know, xy, xz goes to xy, xw, yw, zw, and we give it an initial condition. So we'll give it two self-loop. We'll give it two self-loop nodes as the initial condition, and let's say run this for 3 steps. So obviously, if we just plug this into Wolfram Model without running some sort of a local multi-way system or something, this would choose some default updating order. But if we plug this into multi-way system, we will get all possible updating orders. So in fact, I'm gonna do a bit of rescaling on the graph, give each vertex a reasonable size so you can actually see what's going on, and I'm going to declare an aspect ratio of 1/2. That will make, for some reason, when you have layered digraphs in the Wolfram language, sometimes they lay out in a very kind of squashed format, which isn't very useful. Anyway, so this is what we see. So we started off from this 2 self-loop initial condition here, and then after one step, there was, from the 2 self-loop initial condition, there was only 1 update that could get applied, but then there were 3 possible updates that could have got applied, and so we could obtain these 3 different hypergraphs, and from there were a whole bunch. And you'll see that as well as bifurcations, there are also mergings. So this is another sort of key difference between the multi-way system framework and the Wolfram Model framework and the local multi-way system framework, which is that this global multi-way system framework has state equivalences. So in the Wolfram Model case, that means it has the ability to determine hypergraph isomorphism and to use that as the merging criteria for states in the multi-way system. So the way that works is using some isomorphism functions I developed. So if we call isomorphic hypergraph Q, it takes essentially the same syntax as isomorphic graph Q that's built into the Wolfram language. So if we give it a hypergraph that contains a mixture of arity 3 edges and arity 2 edges, like CB, BA, and then we can ask, is this hypergraph isomorphic? Sorry, that's one too many braces there. We can ask, is this hypergraph isomorphic to 2, 4, 4, 5, 1, 1, 3, 3, 2? And if you stare at that for a moment, you'll realize that these are in fact the same, just A replaced with 4 and E replaced with 5 and D replaced with 1 and so on. So if we call this, then it in fact determines that those hypergraphs were indeed isomorphic. And if we really wanted to, we could find the actual hypergraph isomorphism. This is not as, the output for this is still not perfect. I keep meaning to go back and make this a little bit more helpful, but I somehow never have time. But so it's indicating, for each vertex in the left hypergraph, what are the vertices in the right hypergraph that vertex could be mapped to under some bijection. So this is effectively an association that parameterizes the possible isomorphisms that exist between these 2 hypergraphs. It's worth noting, of course, that in the default case, unless you explicitly override it using the multi-way system options, all hypergraphs, all Wolfram Model hypergraphs in global multi-way systems are treated as ordered hypergraphs, in which the ordering of the elements in each relation actually matters. And so in reality, what we're using as the merging criterion is not isomorphic hypergraph Q, but actually isomorphic ordered hypergraph Q. Which works like that. And so, if we did something like we swapped the D and the E around here, of course, in the unordered hypergraph case, those are still isomorphic, but in the ordered hypergraph case, they're not. And so in that case, you know, if these two hypergraphs appeared at some level in the multi-way system, they would not be merged unless we explicitly told MultiwaySystem that we were dealing with orderless hypergraphs. Okay, so, but as I say, MultiwaySystem doesn't just, the global MultiwaySystem framework doesn't just work with Wolfram models, it works with any kind of abstract rewriting system. So if I give an example of, say, a string substitution system. So string substitution systems are nice because they're reasonably minimal. They show kind of all of the interesting properties that you would expect to see in a multi-way system, but they're very efficient to run because hypergraph isomorphism, as you would expect, is a very hard algorithmic problem, but string equivalence is a trivial algorithmic problem. And so because the main bottleneck in global multi-way system is in fact the equivalence testing, it's the isomorphism testing, it means that string multi-way systems run significantly faster than Wolfram model ones. So for a lot of the things I'm going to demonstrate here, I'm going to use strings as the sort of canonical example. So if I give it a list of string substitutions, AA goes to BAA, BAA goes to AB, and an initial condition, AAA, so this is effectively running, what this is basically giving you is the same result you would have got from a function like string replace list. So it's telling you from the initial condition AAA, there are two, by just applying these rules, there are two possible strings we could get, ABAA, BAAA. Then from those two strings, there are 5 possible strings we could get, and from there, 7 and so on. And so if we wanted to, rather than just seeing lists of those things, if we wanted to, we could see the states graph to see how each of those strings leads to each of the other strings. And so you can see this is nicely laid out in the kind of, with each generation shown as a separate layer, although that won't be true in general for a states graph. It will be true in general for what we call an evolution graph. And I would like to explain the difference between those two cases in a moment. And so as well as giving it lists of updating rules, we can also give it lists of initial conditions. So I don't know, if I do BAA there, then we get a different evolution. And so you can see both AAA as that initial condition and wherever BAA is. Oh, it ended up being a completely separate multi-way system because those two states, there were no states in this one that ever merged with that one, but maybe that would change if we ran it a bit longer, or maybe not. I have no idea what I'm doing. Okay, yeah, there we go. So ABA there ends up being a normal form, and so those two multi-way systems eventually merged. Okay, so in addition to just showing the states graph, which is only showing the particular expressions that are obtained, we could also show things like events. So by default, you'll notice if we just called, if we called multi-way system without any properties specified, then it would show 4 evolution, it would evolve the multi-way system for 4 evolution steps and then show the states list. So that would be the same as if we requested the property all states list. But we could also show something like all events list, and we can see where each event actually got applied. So the way you can read out this event specification, and we'll talk a lot more about event specifications later, but the way that these events are specified in multi-way system is again using kind of the most general format that we could come up with, which is on the left, it's the particular rule that got applied. So in this case, it's AA goes to BAA. Then the second element of the list is what the input for the rule was, which in this case is AA, which is pretty obvious. It's the left-hand side of the rule. But for something like a Wolfram model rule, where instead of it being a literal rule, like for a string, it's actually a pattern rule, then the rule that got applied and the input for that rule will actually be different. One of them will be a pattern, one of them will be a literal. So although in string systems, this is kind of giving you redundant information, for something like a Wolfram model system, it's not redundant. And then the third element of the list is itself a list that contains the prefix and the suffix. So in this case, it's telling you the prefix was null and the suffix was A. So this is a way of saying what we've done is we've taken the initial state, which was, I think, AAA, and then so to the first AA here, we've applied this rule. And then so then there was no prefix, but there is a suffix of A. And again, this is sort of the general format that we use for all of our multi-way systems. So if we took like this multi-way system for the Wolfram model case, and we requested its all events list. Again, it's going to take a moment, but it's specified in exactly the same way. Okay, the rules happen to be rule delayed rather than immediate rules, but other than that, they're essentially the same. It's just that the rules operate on hypergraphs rather than operating on strings. Okay, so as well as actually displaying the events as just sort of in their raw list format, we could also show them as graphics. So we could say evolution events graph. So that would show us essentially the state. It's the same as the states graph that we saw before, but now in addition to just the states, we're also showing these yellow boxes, which are the events. And so for the strings, you know, these events are quite easy to understand. You can see if we take this event here, what it's saying is that the prefix was AB, that there's no suffix, and we applied the rule that AA goes to BAA. And if we did a similar evolution events graph, but for the Wolfram model case, we'd see a similar specification of those events. So if we did something like this, and we did evolution events graph, maybe 3 evolution steps was a bit ambitious. Not only do they take a while to compute, they also take a while to render. I might kill this in a minute if it doesn't render soon. Oh no, okay, it rendered. There we go. Okay, and so now you can see, as well as all of the states in that multi-way evolution, you can also see each individual event. So you can see, so from the dashed lines and from the red lines, this is Max's. This is the event rendering code from Max's set replace framework. So from the dashed lines and from the red lines, you can see which hyperedges have been created, which hyperedges are about to be destroyed. Okay, so then if we go a step further, we could also request not just information about the evolution, but we can also request information about the causal relationships. And again, I'm going to do this for strings first because it'll be simpler and faster. So if we call something like evolution causal graph, now what that's going to show is not just the states and the events and the evolution edges, which are still gray, but it's also going to show the causal edges. So now what this is saying, okay, let me do a simpler case of this, and let me get rid of that redundant thing there. Okay, that's maybe a little bit easier to understand. So now this is, so starting from our initial state here, we could apply these 2 events and we can get these 2 states. And then we're saying for which of the future events have causal dependencies on these previous events. And so those things are shown in orange. So here you can see that there are, we have causal relationships between events on single branches of history. But if we start running the evolution graph, if we start running the multi-way system for a longer period of time and you start getting merges, you'll see that there start appearing causal edges that actually link different evolution branches. And so those are effectively, the fact that you can have causal relationships not just on single branches of history, but between branches of history is how we obtain effective quantum mechanical behavior in global multi-way systems. And I'm going to explain a bit about how that works later on. If you don't want to have all the information about the evolution, if you don't care about the individual states that you reach, you just want to know about the causal relationships between the elements, then you can just call causal graph and you'll get the full multi-way causal graph that parameterizes that evolution. And obviously from the multi-way causal graph, it's always possible for you to reconstruct the evolution causal graph, because just knowing this event, you immediately know what its predecessor state and what its successor states were, because you can infer that from the input, the output, the prefix, and the suffix of the event itself. So essentially all of the information you could ever care about with respect to the multi-way system is encoded in the multi-way causal graph, and all of the other stuff is kind of just is syntactic sugar in some sense. Okay. But as I mentioned, multi-way system is a framework that I tried to design to be as general as possible. So although we've mostly looked at string substitution systems and Wolfram model systems, we could also use it on something like a list system. So if I do 0 goes to 0, 1, 0, 0, 0 goes to 1. Oops, sorry. And I started out from the initial list 0, 1, 0, and I run it for 3 steps, and I request an evolution causal graph. Then we get this thing here, which is, so this is now a list substitution system as opposed to a string substitution system, but in all other respects, the state rendering, the event rendering is the same. And in fact, we get the same result here as if we replaced all the zeros with A's and all the ones with B's. We can show that, it's kind of trivial to simulate list substitution systems using string substitution systems. We did something like this. We get the same evolution causal graph, just with different event and state rendering. We could also use something like a cellular automaton. So in an ordinary cellular automaton, because you're updating everything from left to right and in blocks of 3 cells at a time, there's always one updating order. But in a sense, you can think of each application of the cellular automaton rule as being a separate rewrite event that's taking a block of 3 cells and replacing it with a block of 3 cells where the center cell is replaced, where the center cell can be different and the left and right cells are made the same. So given a cellular automaton rule, you can basically convert it into a list of list substitution rules which replace triples of elements with other triples of elements. And so you can construct by applying either periodic or transmissive boundary conditions, you can construct a multi-way extension of a cellular automaton. So if we take something like Stephen's favorite rule 30, and we started out with initial condition, I don't know, 0, 0, 1, 0, 0. We do something like that. again, this takes a little time because of the event rendering and state rendering, but hang on, if I do vertex size goes to 1, then we see this immensely complicated evolution causal graph for rule 30. Let me actually not do it for 3 steps. Let's only do it for 2 steps. That might be a bit easier to see. So you can see that we started from this state here, the 0, 0, 1, 0, 0 state, and then these are all the events we could apply. These are the other states we can reach. These are the causal relationships between those events. And then that means, unlike in a regular cellular automaton, in addition to doing to just having a single cellular automaton rule, we could also have sets of cellular automaton rules and apply them both simultaneously, or apply the whole set simultaneously. So if we say 170, which I think is the left shift cellular automaton, so it takes the center cell and shifts it to the left, and 240, which is the right shift cellular automaton, and we apply them both, then we get this thing here, which is because left shifts and right, because left shifts and right shifts don't sort of conflict with each other, we know that this cellular automaton is trivially causal invariant. And I mean, if you want to, I'm going to cover causal invariance related functions in a little while, but if you want to skip ahead a little bit, we can indeed verify that that's true. Okay, so other things you could do, I mean, so in addition to cellular automata or lists, you could also run it with kind of built-in Wolfram model substitution system. So if we write out our list substitution system explicitly as a Wolfram model, as a Wolfram language substitution system, then using the built-in substitution system function, then we can do that as well. So if I do something like this, oh, sorry, that was incorrect. I did something wrong. Okay, if I do that, yeah, okay, there we go. So there we're simulating this Wolfram language substitution system, but as a multi-way evolution. Okay. So there are a bunch of these systems that are built into the multi-way system framework itself. There are also a bunch of kind of add-on functions that I've developed that use the core multi-way system framework and that allow you to simulate an even more diverse range of systems that are a bit more specialized. So one example is combinator evaluations. So in combinatory logic, the evaluation order, you can define an evaluation semantics, but the evaluation order isn't sort of defined a priori. So if we define, say, Schoenfinkel's S and K combinatory calculus, if we say S of X, Y, Z, see if I can remember how this works. So X of Z, Y of Z, and then K of X, Y. Oh, we should use rule delayed rather than rule here. So then we do, that goes to just X, and then let's try S of K of S of I of S of K, K of I, something like that. Wait, have I not? Yeah, let's try that. That should do something, maybe. We'll see. Oops, what did I do? I had too many brackets. This is what I get for trying to do experiments on the fly. Okay, what did I do wrong?
The states graph.
Oh yeah, I mistyped states graph. Thank you. Yes, perfect. Sorry, who was that?
It was me.
Oh, good spot, William. Sorry, yeah. Nice one. This was not as interesting a multi-way system as I was expecting to produce. But anyway, okay, you see what happened. So we started off from some expression in combinatory logic. There were 2 possible initial applications of the S and K combinatory calculus, but then eventually, because lambda calculus satisfies the Church-Rosser property, eventually we ended up with a single evolution branch. Okay, but we could also, some of you will have seen Stephen's recent blog sort of bulletin on Rulial space, which used this function I developed called multi-way Turing machine, which takes in a specification of Turing, so an ordinary Turing machine in the Wolfram language is a deterministic Turing machine, where you just specify a single Turing machine rule and it applies it, there's only one place where the event can get applied at each step. But if you have multiple Turing machine rules, there could be different events that could be applied, given a particular state of the machine and a state of the tape. And so, so effectively what you get is a non-deterministic Turing machine. And so I wrote the function multi-way Turing machine to kind of deal with that multi-way case. So if we give it a specification of two Turing machine rules, so 2 states, 2 color Turing machines with indices 2506 and 3506, then we can give it an initial state, an initial tape, which let's give it a 5 symbol tape, and let's again call states graph, and we'll end up, okay, we'll get something that's again very small, so we can't see what's going on. Let's let's try that. Okay, so then you can see these are the possible evolution histories for that non-deterministic Turing machine. Let's run it a bit longer, and let's look at, I don't know, its evolution causal graph. So that might be kind of interesting. So then you can see, again, not only the evolution of this non-deterministic Turing machine, but actually the sets of causal relations between the updating events in that Turing machine. Okay, again, something else that is still kind of under development and is still kind of a kind of pretty hacky, but that I'm kind of, we're interested in getting a more complete version of this working and integrated with the quantum computing framework that I developed. But a very, very early version of our sort of our quantum circuit to MultiwaySystem compiler is also available from the function repository, although it does a bunch of really hacky things that I hope to repair soon. But if we do something like we specify a Hadamard gate, so 1, 1, 1, 1 minus 1, and we give it an initial state, so 1 minus 1, and we request its evolution graph, then we can see the evolution of that quantum circuit. So we're just starting from an initial state vector 1 minus 1, and we're seeing what happens if we apply this Hadamard gate to that system 3 times. And so if we wanted to, we could say include state path weights. And again, don't worry, I'm going to walk you through what these options mean and how what we're actually doing later on. But if I then say vertex weight. Okay, so then at the end you can see, so what include state path weights is doing is it's saying, how many possible paths led to that particular state. So we're weighting each node by the number of distinct evolution paths that led into that state. So you can see there were 4 evolution paths that led into -1, 0, 2 that led into 0, -1, and so on. So if we did 4 times, -1, 0 plus 2 times 0, -1 plus 6 times 0, 1 plus 4 times 1, 0. We'd get 0, 4, which is the same result that we would get if we took matrix power of the Hadamard gate 1 minus 1 and just applied it to the initial state 1 minus 1. If we did that, so if we applied that with multiplicity 3, we'd get the same result. Okay. Anyway, I might talk a bit more about that later. Again, I unfortunately couldn't make it to the live stream bulletin writing session that you guys did yesterday. I'm not entirely sure what you guys worked on, but I understand you were working on these multi-way function systems, which take kind of multi-way systems where the individual elements are integers and where the replacement rules are functions on integers. So to accommodate that, I developed this function called multi-way function system, which takes if you give it something like 2, let's give it a pure function, so given an integer, it outputs 2 possible integers. So let's say take the integer, add 1, take the integer, multiply by 2, add 1, take the integer, multiply by 3, subtract 1. Then we can write that out as a pure function. And then let's start with initial integer 4. Let's start with initial integer 1 and run it for 4 steps. And let's get a states graph. And we get this. And then, again, I'm not sure whether you guys actually covered this in the sort of live stream with Stephen yesterday, but then you can also do things like evolution causal graphs. These get a little bit funky because unlike for something like a string or a Wolfram model or any of these other systems we've investigated, for something like an integer, it's not immediately clear what the individual elements are, and therefore, to determine causal relationships, you have to be able to determine, which events created certain elements, which events destroyed certain elements. So with integers, it's not immediately clear how you go about doing that. In this particular implementation, I decided to use the basic property that all integers have a unique factorization, and so then use the actual prime factorization of the integer to give you the sets of elements. So then what the causal relationships are showing you is which events produced and which events destroyed certain prime factors that appeared in the factorization of that particular integer. Okay. Anyway, so one question you might have at this point is, we have this global multi-way system framework that accommodates all these different system types. How does it manage to be so general? How can the same functions kind of work for such radically different sets of systems? Well, the key is because for all of these different systems, the actual internal the guts of multi-way system are the same in all cases, because all of these different systems ultimately compile down to one single canonical specification, which is a specification in terms of a particular association, which consists of what's called a state evolution function, a state equivalence function, a state event function, a event decomposition function, an event application function, a system type, which isn't strictly needed, but which we use just for bookkeeping purposes, and an event selection function, which by default is the identity. Okay. So then every single multi-way system that I've shown you so far internally is represented using this particular association. So what does this mean? The reason I'm writing this out is because I want to kind of show you how, if you wanted to, you could go about constructing your very own sort of multi-way system format from scratch, just by programming in the kind of low-level machine code that is this association. So the way that it works is the state evolution function is a pure function that takes in a particular state and a set of rules, and it outputs all possible states that could be obtained from that state given those rules. So as an example, let's take, I don't know, string replace list. If we did hash string replace list, A goes to AA, B goes to AB. Oops, sorry. So then that would be a pure function, which if we then applied it to A, would give AA, but if we applied it to AA, it would give AAA. If we applied it, I don't know, to ABA. I'm kind of making this up now. Okay, so that's giving us, so when right at the beginning, when we were running these, when we were looking at these all states lists, I forget where we were doing that, or maybe I deleted the code, but when we took one of these multi-way systems, like if I take, I don't know, this multi-way system, oh no, let's take this multi-way system here, and we run an all states list, all it's doing is applying the state evolution function to each state in that list. So if we take all states list, like that. So it's just being generated by pure application of the state evolution function. So this would be the example of the state evolution function for this particular string substitution system. Then the state equivalence function is the function that takes, again, it's a pure function that takes in a #1 and a #2, and it outputs true if those states are equivalent. So in the case of strings or lists or cellular automata, actually the state equivalence is trivial. We can just use states, we can just use SameQ to determine, you know, are these strings equivalent? Should we merge them in the all states graph? The only real system we've considered so far where there's a non-trivial state equivalence function is the Wolfram model case. And so in that case, our state equivalence function is just isomorphic ordered hypergraph Q. And so that's how we manage the state merging in the Wolfram model case. Okay, so that's the state equivalence function. What's the state event function? So the state event function, just as the state evolution function takes in a specification of a state and a set of rules and outputs all possible states you can obtain, the state event function takes in a specification of a state and a set of rules and outputs all of the events that could be applied. So actually, as long as you, in reality, there's a small amount of redundancy here because as it turns out, given the state event function and the event application function, it's always possible for you to reconstruct the state evolution function. But nevertheless, it's a useful optimization for specifying the state evolution function separately, because in many cases, particularly in the Wolfram model case, running the state event function and then doing the event application function is significantly slower than just running the state evolution function. Okay, so in our case, if I do something like string get string event, no wait, what would it be? Get string state event function. So just to show you an example, if I take the string event function here, and I do that, and I apply this to our friendly state there, ABBA, where did I get the brackets wrong? There we go. That's not good. Oh, this should be a list of states in general. Okay, so then what that's telling us is given this set of rules and given this particular state, this is showing us all the possible events that could get applied. So that's the purpose of the string of the state event function for each of our systems. Then the event application function does kind of the opposite. What it does is, given a particular event, it works out. I mean, again, in the string case, it's kind of trivial because you can just take the output. You basically do a string join of the prefix, the output, and the suffix. So if I do string event application function of that event, it will tell me that this is AABBA, because if I just do a string join of the prefix, which is null, and the output, which is AA, and the suffix, which is BBA, I would get the same thing. So the event application function takes an event and produces the output state that would be achieved by applying that event. System type is just a string. It's a bookholder string, a bookkeeping string that tells you the name of the system you're considering, like string or Wolfram model or whatever. We use that for some internal rendering code, but beyond that, it's kind of it's basically not really considered. And then event selection function is something I'd like to discuss separately, but essentially what the event selection function does is if you don't want to apply all possible events, you only want to apply a particular subset of the possible events, the event selection function is the thing that takes in the specification of all the list of all the possible events you could apply and kind of whittles it down to a particular set of events to apply. So in the default case, event selection function is set to be identity. But if you wanted to, you could set it to be, I don't know, first of hash or something, and then you'd basically get a sequential substitution system because you'd always be applying the first event that could possibly be applied. Okay, so given all of that, let's try to actually construct a multi-way system manually from scratch by using, okay, we're going to use our string replace list event state evolution function. State equivalence function is just same queue. If we ignore the state event function, let's just set that to be identity. In fact, let's do the simplest case. Let's not care about any of the event related stuff. Let's just care about the state related stuff. And we'll call this a string system, and event selection function is going to be identity. And if we then plug that into multi-way system, and we give it some initial condition. So what initial condition should I use? I'll use AB, 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 and then we'll do that 3 states graph. And it doesn't work. Why doesn't it work? I must have mistyped something. That should be a list. And then it doesn't work because we didn't specify any event rendering or state rendering functions. But if oh yeah, that's a useful thing to know. If you're fed up of seeing these nicely rendered graphs, things, you know, when you call states graph or evolution causal graph or any of these other things, obviously all of the nodes automatically get rendered using, you know, whatever the standard system type is. But, you know, in this case, we didn't specify what the system type was, and we didn't specify any of the rendering functions, so it didn't know how to render that states graph. But if you wanted to, for any of these systems, you can explicitly turn off the rendering just by appending the word structure to the end of the property. So if you, instead of calling evolution causal graph, you can call evolution causal graph structure, and then it will just show you the graph without any fancy rendering. And actually often that's quite useful if you want to run things quickly, because particularly in cases like Wolfram model or cellular automaton, the rendering is really quite slow in comparison to the multi-way evolution. Okay, so then, okay, calling states graph structure, for our manually coded multi-way system, we ended up with this. And just to check that we did actually do this correctly, we can compare that against the built-in string substitution system framework. So if we do A goes to AA, B goes to AB, for initial condition AB, 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 3 states graph structure. Hopefully, fingers crossed, we get the same thing. Yes, okay, that looks pretty much the same. All right, okay, so then I already mentioned about sort of possible updating orders and ways that you can select possible updating orders. So suppose you're not interested in, is this a good example? Yeah, this is a reasonable example. If I do A goes to AA, B goes to AB, the same example we treated above, and then we consider the case like this. So if I look at the multi-way causal graph for that, this is showing the causal, you know, the multi-way causal graph for all possible updating orders, but maybe you don't care about that. Maybe you just care about the causal graphs for a particular updating order. Well, then what you can do is, rather than requesting causal graph, we can request causal graph instances, and that shows you essentially for every possible path. If we look at the evolution causal graph, what causal graph instances is doing is it's traversing every possible path through the evolution causal graph, and it's looking at all of the causal edges that you hit. And then, it's looking at all of the events that you hit, and therefore all of the causal edges you kind of pick up by peeling off all of these different possible updating orders. And then it's just showing you a big list of all the possible single event history causal graphs. And, in this, even for 3 evolution steps, there are quite a few. If you want to limit the number of ones you're shown, you can just use max items goes to like 5, and it will only show you 5. Okay, sorry. So then if we consider doing, if we take, say, the string substitution system ABA, AA goes to B, and we do, I don't know, AA, BAA. So in addition to just having a states graph, so with a states graph, if you have, this is probably a bad example, actually. Let me see if I can think of a better example to illustrate this. What we want is a string substitution system that doesn't just grow. We want something that also shrinks. Okay, I'm going to try and invent one in real time, which may not work so well. So if I do an ABA goes to, no, that's kind of boring. If I do that, is that going to do anything interesting? No, is the answer. Okay, forget it. Let's just treat this case. So in the ordinary states graph, because of the presence of the state equivalence function in this in the association, any states that end up being equivalent with respect to that state evolution with respect to the state equivalence function will end up being merged in the states graph. But there might be cases in which you want to kind of switch that off in some way. So then there are a bunch of ways you can do that. One of them is to consider this thing that we call the evolution graph. So the evolution graph doesn't merge. So what will happen is the evolution graph will go through the evolution of the system one step at a time, and it won't merge states that appear on separate sort of evolution steps. So if you have an occurrence of, say, AA that occurred at step 1 and an AA that occurred at step 2, if you're requesting the states graph, they'll get merged, but in the evolution graph, they won't because they're on different time steps. But in the evolution graph, as it's normally constructed, they will still get merged if there are multiple states that are the same, that appear on the same time step, then they will be merged. You can switch that off by requesting evolution graph full. So, or evolution graph, okay, right. Evolution graph full, what this is doing is it's showing all possible events that could be applied. So in the ordinary states graph and in the ordinary evolution graph, sort of all equivalent event instances are merged. So if you had a particular state A and another state B, and there were sort of two possible ways of getting from state A to state B, in the default states graph, that would just be shown as a single line. But if you wanted to see all the possible ways of doing that, you can request the evolution graph full. So effectively, this is refusing to merge equivalent events. There's a way you can do that in the states graph as well, which is by setting an option which is called include event instances. Goes to true. That gives you the equivalent way of doing that just using a states graph. If you wanted to if you wanted to turn off merging, not just for events, but also for states, then you could request the evolution graph unmerged. And so now nothing is getting merged. Anytime there's two independent evolution events, that not only are they shown as separate edges, but they also yield separate states, even if those states are actually equivalent. And if you wanted to, instead of showing these things as multi-edges, these sort of event multiplicities as multi-edges, if you just wanted to kind of weight each evolution edge by the number of independent events that sort of correspond to it, then we can request the evolution graph weighted, in which case now if we switch on vertex labels, say vertex labels goes to vertex weight, then now you can see, this was an incredibly boring example. Can I think of a better example? Because these all have weight 1. That is so dull. Okay, hang on, wait, do we have any better ones? Maybe this one will work better. If I do 3 evolution graph weighted, vertex labels, vertex weight, see what we get. No, we also get a really boring thing. That is rubbish. Okay, there are definitely examples of this in the documentation that I found where it gives something non-trivial. If you want to see a demonstration of how that works, go look in the documentation. But I don't have the intelligence to construct an example of that off the bat. I thought this one would work, but for some reason it didn't. Anyway, okay, that's what happens. So in addition to the evolution graph stuff, what we could do, so it's not just evolution graphs that can have non-trivial weights of vertices and edges. We can also consider, oh, no, I know what I did. I did something really stupid. It's not the vertices that are labeled. Edge labels goes to edge weight. There we go. Okay, that's what I meant to do. So here you see, so this event had multiplicity 2. So in this case, in the case of the evolution graph full, it showed up as 2 separate edges. But in the evolution graph weighted, it shows as a single edge with weighting of 1, with weighting of 2. Sorry. Yeah. Okay, that's what I wanted to show. The world makes sense again. Okay. So now, if we consider, instead of having weighted evolution graphs with weighted edges, we can also consider weighting the states graphs with weighted states. So if we take something like A goes to AA, B goes to AB, AABA, BAA, and then we do 3 states graph. Okay, so that's the states graph that we see. Then what we could do is there are many different possible ways we could weight this states graph. So one immediate way we could do it would be by saying include state weights goes to true. So what that's going to do is it's going to say, so for each layer in the states graph, sort of what proportion of all of the states that appear on that layer is this particular state. So in other words, if we didn't do any merging, what proportion of the full unmerged states graph would correspond to this particular state? So if we do that, and we actually switch on the vertex labels this time, then we could see, okay, so in this case here, in the full unmerged states graph, there are apparently seven different states that would have appeared at level 2 here, of which 3/7 of them are this state, 2/7 of them are this state, and 2/7 of them are that state. And I'll show you in just a minute how you could go about producing the fully unmerged states graph if that's what you wanted to do. But that's only one possible way that we could have weighted this thing. We could also have included state path weights, which would do what I think I showed you just earlier, which is now the vertex weights are demonstrating how many independent evolution paths would have led to that particular state. Okay, so now, what if you're given a multi-way system evolution and you want to determine properties of its causal invariance, or you want to determine things about its branch pair resolution time, or things like that? Well, both multi-way system has, okay, the multi-way system framework has a bunch of built-in functions for doing that, and I've also developed a bunch of helper functions also in the function repository that do that in a kind of more specialized way. So let me begin by showing you some of the helper functions. If we take, actually, yeah, okay, no, let me not use that system. Let me use a different system. So if I call the function branch pairs, and I use the system like A goes to ABA and AA goes to B, and I call AABAA 2, I can see, once it loads the resource, so I can see for this multi-way system, what were all of the branch pairs that got produced within the course of its evolution. But some of these are branch pairs that will kind of resolve very quickly, and some of these are branch pairs that might not resolve at all. So if I wanted to, I could request branch pair resolutions, and I could, and what I should get back is an association that tells me which of these branch pairs have resolved and which ones have not resolved after 2 steps. If we run it for another step, again, it might take a little bit of time because this is quite a complicated multi-way system. But again, we can see some of those branch pairs are resolved, but a lot of them have not. So I'm going to go ahead and guess that this particular multi-way system is not causal invariant, because this signature of the resolution of the branch pair resolutions list being much smaller than the branch pair unresolved list is usually indicative of a non-confluent system, and hence a non-causal invariant system. So if I now take this and I run causal invariant Q, it will complain at me for some reason. And it tells me it's false. Okay, so this is indeed a non-causal invariant system. Okay, but I could also have done all of those things within multi-way system itself. So if instead of running this, I called multi-way system branch pairs list, I would have got the same result, and I could have called branch pair resolutions list, and that would have failed. Branch pair resolutions list, and it would give me the same result as here, and I could also call causal invariant Q, and it would give me the same result as it would if I'd called the external function. So multi-way system has all kinds of built-in properties for determining things like causal invariance, branch pair resolution time. It also has ways of determining Knuth-Bendix completions. So this comes onto an interesting question of sort of the relationship between the quantum mechanical aspects of global multi-way systems and the quantum mechanical aspects of local multi-way systems. So as I'm sure Max kind of mentioned in his talk yesterday, you know, one interesting thing that can happen in local multi-way systems is you get interference between different branches that essentially occurs because you have 2 hyperedges that are purely branch-like separated, but that they can nevertheless be kind of pulled into a single updating event. And so you get a new state that is somehow an interference between those 2 different branches. In the global multi-way system, by default, that doesn't happen because the only events that get applied are the ones that apply to a particular state and not sort of between pairs of states. But as I also mentioned in my quantum mechanics lectures, you can induce interference kind of in a post hoc way by performing a Knuth-Bendix completion. So by analogy to the local multi-way case, if you consider the situation where you have 2 states that are separated, sort of branch-like separated at the level of a single hyperedge, instead of just pulling both of those hyperedges into a single event and applying that, the global multi-way way of doing that, of imposing that interference, would be to say, add in a completion rule that allows you to hop from that hyperedge to this other one and back again. And so, and this will give you again an interference effect between those 2 branches, which is which again, assuming the whole kind of that our physics project's interpretation of how quantum mechanics works is correct, should give you the same result as it would do if you had kind of direct local multi-way interference. So we should be able to. I mean, I don't know how slow this is going to be, but we should be able to demonstrate that explicitly. just by using global multi-way system. So if we call Knuth-Bendix completion, it's going to take a moment to compute that. But what it will do, in fact, I should have not done that. I should have done this. I should say completion equals that, so that we actually have the ability to store the completion rules that get generated. So what this is going to do is it's going to generate the kind of the minimal completion list that's needed to guarantee causal invariance of the system. So in effect, what's happening is anytime you have hyperedges here that are distinct from hyperedges here, it's adding in rules that allow you to jump from a hyperedge here to a hyperedge here. So it's almost like it's imposing these the branch-like separated events of the local multi-way system as a kind of post hoc step by performing a Knuth-Bendix completion. So that's our list of completion rules. So if we collapse that down because it's a bit ugly, if we now go back and we take our original multi-way system and we add in, let's say, join that with completion, and we give it a moment to run, it will take a little while because this is quite a complicated system and global multi-way systems are reasonably slow. But in a moment, it should produce the version of this in which there is effective branchial interference, and which we can think of as being like the observer is performing some measurement event, or is performing some measurement operation that is causing, in their interpretation of the world, which is causal invariant, it's resulting in in interferences between the multi-way branches that would not have been seen if the observer hadn't chosen to make that measurement. This is taking longer than I would have expected. I'm going to give it 30 seconds, then I'll kill off. Oh, no, okay, we're good. Okay, now, yes, cool. Now we have, so we end up with a states graph that looks a little bit different to this one, because now there are these new events that allow you to effectively hop from one branch of history to another by using the completion rules. And so these new states that you can obtain by the fact that you're able to now effectively hop between these different branches, to hop between hyperedges that lie on these different branches, those new states are the effective interference states that exist between those branches of history. And so our conjecture is those are the same as the kind of branchially separated events that you could apply in the context of a local multi-way system. And I believe Hatem's project is actually going to try and formulate that conjecture and possibly prove that conjecture in a slightly more formal way than the way I've expressed it here. Okay, so what I'm trying to show you is that, in addition to just computing branch pairs, you can also compute things like Knuth-Bendix completions. And again, there are all kinds of helper functions you can use in order to do that. So this is an example of a Knuth-Bendix completion you could apply to a string substitution system. So if you want to test aspects of quantum mechanics, but you don't want to bother to go through all the computational effort of actually simulating a full multi-way Wolfram model system, you can try out all of these completion steps, all the branch pair stuff. You can use that with any other kind of multi-way system, be it a string system, list system, cellular automaton system, Turing machine, whatever. Okay. But you'll have noticed that for all of these branch pairs and these causal invariance testings, I've had to specify explicitly kind of what the input state was. But there's a notion of kind of canonical branch pairs. So given and so canonical branch pairs are branch pairs that exist kind of independent of the initial conditions. They are the minimal set of branch pairs that you need to sort of consider in order to evaluate properties like global confluence and causal invariance. So let me show you what I mean by that. So if I just give you, if I say canonical branch pairs, and I request, let me do this substitution system, AA goes to ABA and AAA goes to B or something. And then I run that. Okay, it's going to show me this list. So what does this list mean? Well, you can see I just specified a string system. I didn't actually specify any initial condition. So this is the set of branch pairs that exist independent of the initial conditions. And the way that canonical branch pairs works that out is it looks at the left-hand sides of all of the rules and it computes the overlaps. It computes where could there exist ambiguities. So again, to use the kind of formal mathematical logic parlance, what it's doing is it's computing critical pairs in order to make that determination. And then it's showing you the minimal set of critical pairs that exist for that replacement system. So and that's something you can do even without knowing the details of the initial condition. And then if you wanted to, if we run canonical branch pairs but with a time step, it will even tell you which of those canonical branch pairs resolve and which don't resolve after a certain amount of time. And so what that means is that in addition to doing causal invariance testing, which is testing for causal invariance for a particular initial condition, we can also do what we call total causal invariance testing, which is determining is the particular rewrite system you specified causal invariant independent of which initial condition you specified. So in effect, what it's doing is a global confluence check to determine, given the set of canonical branch pairs, do they all converge within a certain period of time? So in this case, we can see actually just by looking at the canonical branch pairs that this is not globally confluent and hence can't be causal invariant. And so we can see that explicitly if we run total causal invariant Q. And it tells us indeed that it's false. And again, just like with the ordinary causal invariance testing functions, we can run all of these functions, these helper functions, either as separate function repository entries or as properties within MultiwaySystem itself. So if I wanted to, I could use MultiwaySystem, and without giving it an initial condition, I could say 2, total causal invariant Q, and it would tell me that this is not a causal invariant system. Now, you may wonder, why do we have to specify a time step at all for doing this causal invariance testing? That's simply a consequence of the fact that I mentioned multiple times, I think in my third lecture, that because the word problem on finitely presented monoids is undecidable, we know that causal invariance testing and all the things that are involved in it, like global confluence testing, those are all undecidable problems in general. So if we just had a pure total causal invariant Q function, it would not be guaranteed to terminate in general, and that's not really a good thing. So to get around that, I said, let's add in a time step that is, or a time stamp that says we'll evolve the system up to a particular point, and if it's still not causal invariant by that point, we're going to assume it's not causal invariant. So that's effectively what that's doing. Now, if you want to do more sort of in-depth causal invariance analysis and branch pair analysis, there are various other things you can do. You can include things like predecessor states and successor states. Let me show you how that works. So if we take a set of branch pair, what did I just do? Okay, we take a set of branch pairs like this. If we wanted to, we could look at what were the predecessor states. So in other words, what were the states where there existed a rewrite ambiguity which yielded that particular branch pair, which I can give just by setting give predecessors to be true. So that will tell me that. So this is telling me that in the multiway system, AA BAA bifurcates to yield this particular branch pair and this particular branch pair and so on. And then if I wanted to, I could look at the resolutions, as I was doing before. Then we could ask, in addition to showing us, as before, we could tell it to show us the particular predecessor states. We could also ask branch pair resolutions to tell us the resolvent states. So for the branch pairs that resolved, what common state did they resolve to? So we can say give resolvents goes to true. And now what it's going to tell us is this particular state, AABAA, yielded this branch pair. And then eventually after 2 evolution steps, or after a maximum of 2 evolution steps, this branch pair reconverged on a common state, which is AABABAABA, and things like this. And so you can start to look at, essentially what were the shapes of the diamonds that existed in the multiway system that are associated with branch pair resolutions and things like that. Okay. So then, and again, just to show you the sort of the extensibility of this. So if I do canonical branch pairs, so now if I give it, instead of a string system, let's give it a Wolfram model system. So this is going to be a much more algorithmically complicated activity because what it has to do is effectively, determining string overlaps, doing critical pair testing in strings is relatively straightforward. Determining hypergraph overlaps is a bit more complicated, but nevertheless, canonical branch pairs can do that pretty quickly. If we wanted to, we could, I mentioned again in my third lecture that one often makes a distinction between the existence of non-trivial critical pairs and the existence of trivial critical pairs. So a trivial critical pair is a situation where you have a single element that can be rewritten in 2 different ways to yield the same element. And so within functions like canonical branch pairs or canonical branch pair resolutions, you can request it to also include the trivial critical pairs by saying include self pairs goes to true, which I think in this case will give it, so okay, in this case there were a few self pairs that kind of got culled in the default, but which we can now specify explicitly. Okay. So given information about things like branch pairs and their resolutions, we have all the information we need to be able to construct information about the geometry of branchial space. In other words, the geometry of the space of quantum states. So to do that, let's take one of our multiway systems, and let's do, again, let's take the strings case because it'll be faster. Let's do A goes to ABA, AA goes to B. Let's start with AABAA, and let's do 2 steps, and let's request its branchial graph. Okay, so we're going to get a branchial graph. What's this showing you? Well, it's showing you, so it's effectively showing you the ancestry distance in the multiway evolution graph. If we take the states graph of this, what this is telling you, this is showing you a particular branch-like hypersurface through the multiway evolution graph. And so it's telling you, if a pair of states are separated by a single branchial edge, then they have a common ancestor distance of 1. If they're separated by 2 branchial edges, then they have a common ancestor distance of 2, and so on. if we want, so by default, branchial graph only shows you the collection of states that are bound in branch pairs that did yield, that were the consequence of ambiguous updating events. Of course, in general, there could be states that were achieved by just following a single evolution branch, in which case there's no ambiguity. They don't live in branch pairs, and branchial graph won't show you that by default. Although again, just like with all of the other defaults in MultiwaySystem, there is a way to override it. You can just say include full branchial space goes to true, and that won't do anything. This is probably a bad example to try. Oh, let me try that. No, again, a bad example. Can anyone think of a better example? Okay, no, actually I have an idea. I think I know a better example. This would be a better example. A goes to AA, A goes to AB would be something good. And then if we just start it from a single state, A, try that. No, that didn't work either. Ah, I know what we can do. We can cheat. We can do that. Okay, yeah, that'll work. All right, that's going to illustrate my point a bit better. So if we didn't include full branchial space, this would just show you this branchial graph. But because we've included this kind of trivial updating event here, this doesn't produce any branch pairs because the state is always the same. So by default, those states are going to be left out of the branchial graph, but we can include them by using include full branchial space. Okay. So let me now show you some things about, I mentioned before I was going to go into a bit more detail about the distinction between states graphs and evolution graphs. So let me now do that. So if I do, let's try another multi-way system. Let's again do a string substitution system. What should we use? Let's use the same one. No, let's not use the same one. Let's use this one. Let's use AA. A goes to AA. B goes to AB. And let's do ABA 3 states graph. I keep misspelling states graph. This is bad. Okay, right. So this is our standard grid-like multi-way system that's used in all of the documentation examples because it behaves really nicely. So if we now, if we take this thing and we look at its all states list, you can see that, you know, by default it's merging all of the possible states. But one thing that we might want to do, and okay, and actually again, if we look at its all events list, it's doing the same thing. But suppose now we wanted to say, don't merge states that appear on separate time steps. So in this particular case, it won't make any difference. But if we also wanted to say, don't merge any states at all, the way we could do that is by saying include state ID. Okay, let me just show you this and then we'll explain how it works. So if I say include step number goes to true, include state ID goes to true. So now what we get is a completely unmerged states graph. And the reason it's completely unmerged is because by saying include step number goes to true, we're saying every state has its associated step number. So what that's telling you is that if you have two equivalent states, but they exist on different, if they exist at different time steps, they were generated at different time steps, so they have different step numbers, then they don't get merged because same queue will not return true in that case. So in other words, what the evolution graph is doing, the reason why the evolution graph differs from the states graph is because the evolution graph includes step numbers by default. But what we're also doing in addition to including the step numbers is including the state IDs. So what the state ID is effectively a UUID for each individual state. So now because the UUID is unique, none of the states can get merged because none of them, for no pair of states is same queue going to return true. Even if the individual strings are true, are the same, the UUIDs will be different and so they won't get merged. So let me show you how that works internally. So if we say, if we just did include step number goes to true and we requested an all states list, then now you can see we have 0 goes to ABA, 1 goes to AABA. So so effectively each state is now specified by a rule that has the step number on the left and the state on the right. If we just included the state IDs, then it wouldn't include a step number, but it would include, so the step number is going to be set to automatic, but it would include a UUID, which is just this string of numbers. And if we include both a step number and a state ID, then you can see both things are incorporated. And so if we showed the events list, the UUIDs and step numbers also propagate down to the events. So essentially how the events work is through something like a sort of hashing system where what the event is, the ID for the event is a list containing the state ID for the input state and the state ID of the output state. And so this means it's still possible for your event application function to determine what the input state was and the output state was, including the step number and the state ID, because it can just take the first element of the event ID or the second element of the event ID, respectively. I'm aware I'm just about out of time, so and there were a bunch of other things I wanted to show you. So maybe those will come up in discussion or in questions. But just before I was going to show you some stuff about how you can construct your own rendering functions and some other customizations you can do to incorporate your own kind of code into MultiwaySystem. But just before we wrap up, let me show you kind of a couple of different variants of this system. So MultiwaySystem, the regular global MultiwaySystem applies both space-like separated and branch-like separated events, and it demonstrates both. So both separations are shown. So for instance, in this case here, in the case of A goes to AA, B goes to AB, even though there are actually there are no purely branch-like separated states, or no purely branch-like separated events, because every place where this could get applied is either at an A or a B, and there's no overlap between A and B. So in other words, everything is purely space-like. There's no real branching. The only branching that appears is the trivial space-like branching. So one thing you could ask is, can we construct a MultiwaySystem which doesn't show any of the space-like branching? It only shows the branch-like branching. And so the answer is yes, and it's this function I developed called generational MultiwaySystem. So if we run generational MultiwaySystem on this, you will see, hopefully in a moment when it wakes up and imports the okay, there we go. Now it's working. Right, so generational MultiwaySystem for the same system, you'll see doesn't have any branching, because what generational MultiwaySystem is doing is it's taking the input and it's applying not just a single event at each step, but it's applying the maximally consistent set of space-like separated updating events. So in the generational MultiwaySystem, you know that all of the bifurcations that exist are bifurcations that exist purely because of branch-like event separation, rather than a mixture of branch-like and space-like event separation. So in the generational let me construct a generational MultiwaySystem where there definitely is branch-like separation. So if I do AA goes to BAA, BAA goes to AB, for instance, and I'd say bah, like that. I do this. Okay, so there we have a generational MultiwaySystem where you can see, so each of these bifurcations is a bifurcation that exists because there was an ambiguity there was effectively an overlap between the inputs for the events, not just because they happen to be space-like separated. If we want to we could see the all states list for that, or we could see the all states list for this, or something like that. So if you want to reproduce behavior that's more like that's kind of, if you want to reproduce something that's showing you the purely quantum mechanical behavior of the system with none of the kind of space-like separated stuff, then generational MultiwaySystem is the function to do that. There are also some functions that Stephen and I developed for doing kind of more pleasant rendering of some of these substitution systems and multi-way systems. So we have this function that's multi-way evolution plot that's kind of, if you want to reproduce some of the pretty pictures that Stephen has in his technical introduction, many of them were, for the case of multi-way systems were produced using multi-way evolution plot, which is a way of showing you, if we do evolution event rendering, goes to positional polygons. Okay, oh, sorry. Then, so this is an example of a multi-way evolution plot for that. So this is a way of showing explicitly where each event got applied, what the input for the event was, what the output for the event was, and what the overlaps are. You can, so the explicit overlaps are going to be highlighted with these darker gray regions where these two events happen to overlap with each other, sort of, which you can see geometrically by looking at the positional polygons that show where the events got applied. So there are some also, so in addition to some nice helper functions which do cool algorithmic things, there are also some nice helper functions which do cool rendering things. Again, a complete list of these things is shown on the Wolfram Physics website under the tools guide page, which actually is currently a little bit out of date because it doesn't include several of the functions we've developed more recently, but hopefully will be being updated in the next few days. So I'm aware I should probably stop talking right about now. So let me stop sharing. And if there are any quick questions before the session ends, I'm happy to take them now.